Thank you very much. It's great to be here. I am Jonathan Neufeld, president of IO Aerospace. I appreciate the audience here. This is fantastic. I really enjoyed the day learning about quantum and the intersection and all this information we're talking about. And I'm going to talk a little bit about something different. We are an advanced remote sensing firm. And as they said in the intro, we do use a jet aircraft, which is very cool, and I'm going to get to that. Our main application, of course, is vegetation encroachment. And utilities across the US and Canada spend on average between $6 and $8 billion on vegetation encroachment work every single year. It's one of their largest line items, right? And when you think about that, it makes a lot of sense. Grid resiliency, all the various applications. It's something that we need to pay a lot of attention to, and something that we're obviously very interested in. Right? In the past couple of years, we've seen the consequences of poor vegetation management. We've seen the consequences of grid resiliency when it comes to floods and fires and all the effects of our changing climate and this changing world. When you think about the world of vegetation management, though, it's evolving very quickly in the same way that most of the technology we're talking about here is evolving very quickly. Right? So in the old days, the trick was you would send someone in a truck. They would go look at the lines and say, oh yeah, there's a tree there. We should cut that. And they'd write it down. Tree here, intersection, right? No tree there. Good. Drive to the next spot. It's incredibly cost inefficient, and it's incredibly dangerous when you think about the number of miles on the road to do that kind of work. And so over time, they were like, well, this is goofy. Let's stop sending actual people to the field. We have cool things like airplanes. We can collect interesting data. We can do something different with that, right? And so people started turning to LiDAR. How many people are familiar with LiDAR? You guys use that? Oh, I love this crowd. Oh, you guys are the best. So LiDAR is amazing, right? It's high definition, it's super detailed, it's incredibly accurate. The only downside to LiDAR is that it's really expensive, and it's occasionally really slow. It takes a long time to deliver, right? You get to know a lot about a very little part of your network. So as long as you know where to look, LiDAR is a great tool. And then, of course, the other sentiment was, well, let's look at satellites. We have all these satellites up there. You know, they're producing gigawatts of energy, or sorry, gigawatts of imagery every day. It's absurd how much they produce. Let's start using those. But take a look at this image here and tell me if you can find the power line in that. That's a standard 50-centimeter image from a standard commercial provider. It's incredibly low resolution, and it's hard to use that to make reasonable and intelligent decisions about your network, right? This is an image we took of the same area using our aircraft and our specialized camera system, right? This is a 10-centimeter image versus a 50-centimeter image, right? Suddenly, you can start to see a whole lot of detail and a whole lot of information, right? There's the poles, there's the wires. We can always spot them every single time. The level of information and detail you can pull out really leads to better information and better decisions. So this is our beautiful aircraft. This is what we've created. This is one of our key tools in mapping entire utility networks all at once and providing incredible intelligence and insights back afterwards. Our lovely host here talked about the work we did in configuring it, and you can see the square boxes on the side. So we actually had to cut enormous holes right through the aircraft, build in those payload bays, and now we can carry multiple sensors and systems with us. We can carry methane detection systems, which we've done for the likes of MethaneSat and the Environmental Defense Fund, and we have our unique camera system, which we also carry there. In the world of remote sensing, it's insane to use a jet. Most people use like a Toyota Corolla with wings. It's cheap to operate. It's easy. Anyone can do it. But they fly low and they fly slow, and it takes a long time to get that information. With this jet, we're flying at 30,000 feet at 700 kilometers an hour. We can image a square kilometer every second. Right, a square kilometer a second. It's absolutely bananas. And so what do we do with that? Here's a good example. So we were recently flying some work in Manitoba. We're able to fly incredible long distances all at one time and cover enormous amounts of territory. So this is about 8,000 square kilometers that we imaged in this single flight. That was a 4-hour flight, 8,000 square kilometers. Do 2 of those a day when the sun is nice and high, and now you're capturing unbelievable amounts of data. This is what lets us do entire networks very quickly. One of the other key things I love to talk about is because of the resolution of our image, we can find the poles, right? If you talk to folks who are doing satellite, they can't see the poles in the imagery, and so they trust the network. And again, with all due respect to the utility folks in the crowd, you're very good at knowing approximately where your stuff is, but not knowing precisely where your stuff is, right? And so this is an example from a project we did in Alberta. You can see in the left-hand side, the yellow image or the yellow line is what the utility told us, and the red line is what we actually found, right? So there was a 30-foot difference, 10-meter difference in where the lines actually were versus where they said they were. Now, in this example, it doesn't make a difference, right? It's a big grassy field. But imagine that there's a whole lot of vegetation along the edge of that road, and your line, you think your line is 30 meters difference, right? It's going to give you a very different result in the end. So by being able to find every single pole every single time, we're able to provide much more detailed analytics and much more reliable outcomes when you're making that $6 to $8 billion decision every year of what do I cut, what do I deal with, what do I prioritize. Here's an example again from another project we've done. This is one small area of a network from a recent project. There's a couple things going on in this image. So the red, green, yellow gives you a quick indication. Is this square kilometer something I really need to pay attention to? Is this square kilometer something where I don't need to pay attention to? That color coding was based on input from the utility who requested this to say if it's over X number of potential conflicts, please flag it and we'll look at it. If you look at the lines, they're color coded as well by potential conflict, and that's on a span by span basis, right? So every single span gets a measurement. Every single span gets a rating, and then we're able to give that information back in a very detailed way. The goal here is to triage resources. So I'm not going to say that we can take the place of LiDAR or that we can take the place of someone driving around in a truck and looking at the actual trees, because we're 30,000 feet up. But we can help companies very quickly prioritize where to send the next level of resources, look at it with their LiDAR, look at it with their mobile scanning, or send their person in a truck. Here's a detailed view. So as we dig into the details now, you can begin to see the number of conductors in each span. This is our vegetation distance mask, so you can get a sense of how close the vegetation is in each one. In the very bottom there, you can see the line is purple, which means it's actually touching, and the veg mask matches. So that's a measurement we're doing with all of the data that we've collected, all of the data that we're able to use and put together into this model. And then to be able to extract this analytics outcome. Here's another one. This is an actual image of ours with the similar colored heat map on top. So you get a really good sense there of how close the vegetation is to those lines. And it's interesting, we've cut it so it's nice and tight along the power lines because that's what they typically care about. The goal here again is to help triage resources, help people make the best possible decisions on a network-wide level, so you get a sense of what's happening and a sense of the risk and the resiliency of your network. And here's a great one. This is in 3 dimensions now because it's 3-dimensional information, right? The number of images we capture let us build these 3-dimensional models, and now you can see it in 3D, right? We can see the poles. Those poles are manually extracted from every single image to make sure they're absolutely correct. The wires are modeled based on parameters that we get from our utility partners, or the engineering firms, or the veg management teams that we work with. And then the analytics provide the insight about what to do and where to go, right? So it's very clear. You can see in the one in the front of the image there's a red field next to those conductors. It tells you the size, the scope, the potential conflict. These analytics are helping utilities and engineering firms make decisions around network resiliency, around vegetation management, about where to place those resources, how to use that time and money. And the really cool thing is that it's network-wide, right? So if I go back to the person in the truck, if I go back to the fixed wing or the helicopter LiDAR, you're able to do a small part of your network every year, right? The traditional model is you break it into 5 chunks. Every year you go to a different chunk. You don't worry about the other 4, but there might be something going on in one of those that potentially you're not aware of, right? By doing it network-wide now, it gives you a quick sense of what's going on, how to make those decisions, and a really detailed view into what's going on as well. We had an independent field review done. One of our clients took our information, drove out into the field, checked something like 250 spans, wrote it down on a clipboard, and came back to us. And he phoned me up at the end of the day. He's like, I just checked 60 spans today. It was unbelievable. He's like, I only found 2 errors in that entire time. It was amazing. And he said they were errors, that were within the sort of tolerance of margin of error, pardon me, where we said it was, a meter and a half, and it was actually 2 meters, something like that, where it was just on the other side of one of those color boundaries. So the results have been field tested. We're getting feedback from clients and partners. We're getting real-world verification of what we're doing, and it's amazing to get those kind of results back, to know that we're able to hit these sorts of numbers, flying at 700 kilometers an hour, 30,000 feet up in the air. It's unbelievable. So the last thing I want to leave you with here is this combination of things, right? So the first step is the ability to collect wide areas very quickly, super high detail, super high resolution. The next is the ability to run analytics on it, get a good and detailed sense of what's going on, what's happening across the entire network, and provide the ability then to triage the resources into those zones, right? And then the third one is those detailed analytics on a span-by-span basis that give the clients and the users the ability to know what's happening in detail across their network, right? It's a powerful combination for us. We're finding really engaging traction. We're finding a lot of interest from engineering companies, vegetation management firms, utilities, and it's a unique offering. So something we're very proud to have built up. It's interesting, we're talking with the Quantum City folks and others about the introduction of quantum computing into this process. We're talking with people about the introduction of AI and artificial intelligence to be able to further deepen and improve our analytics, to be able to get more out of this information that we're generating. And I think there's a tremendous opportunity on the horizons. And I'm excited to be here and be able to share it with all of you. So thank you very much. If you have any questions, I'm happy to take them. There's a question in the back, if we can get him a mic. Yeah, I love this question. So 1 kilometer per second, we do anywhere from 8 to 10,000 square kilometers in a flight. That works out to between 4 and 5 terabytes of data, right? And for any of the imaging folks out there, we collect RGB, red, green, blue, as well as near IR. And the near IR gives us the ability to do vegetation detection, vegetation health, those sorts of analyses. How much is that in terms of kilometers of distribution line? That's a good question. It really depends on the network density. So if we're flying a metropolitan area or a suburban area, it's a very high number. If it's a rural area, it's much lower. So it's a hard one to answer without getting a look at the network, but it depends on density. How much time to do a network of 100,000 kilometers? Boy, that's a good question. Probably take us about a month to fly all of that. Pretty fast for something that size. Yeah.
There's a company in Nova Scotia called Detect. They use drone to do something exactly like this. Then how compares the data from the drone to the data that you guys are getting? And from how accurate is
yeah,
those data?
Good question. So I love drones. Because they're really good at things that are very close to where the operator is, and they can do it in incredible detail, right? So the downside of drones is their ability to cover large areas. Drones could maybe do 5 square kilometers, 10 square kilometers in a day, if you were to put them on a mapping pattern. And where we can do 10,000 square kilometers in a day. But the advantage is they're going to get a 1 centimeter pixel, so it's going to be much more higher resolution than we are, and it's going to be much more accurate than what we can do. So the best way it can work is we would come in and map the entire network. You'd get those squares, red, yellow, green, and then you could say, well, this one's red, or this one's, has a lot of potential conflict. Let's send in some drones, have a look at that infrastructure, and make sure we know what's going on there. Get a super high resolution view of it. So they tend to work in partnership. Awesome. Thank you very much. Appreciate it, everybody.